Okay, thank you for your introduction, Harald. So this is a joint work with Pereg and Holger Boche. And I thank, of course, the organizer for this, the organization of this conference. And also Uzi, my co-author, he is at the Slack. So if you have short questions during the talk, he can answer it in the Slack immediately. I think Anka told me before there's some slight delay in the transmission. So sometimes perhaps it's good then to ask just questions in the Slack. So we make good experience with this in a conference in March. So what we want to consider a broadcast model. So we have one sender who want to transmit to two receivers. The sender is called Alice, and we have here Bob1 and Bob2, and we will consider classical channels, and we will consider quantum channels. And the special thing is that Bob1 and Bob2 shared an entangled state here. And the first reason why we considered this is because last year there were results for the dual channel where you have two senders and one receiver. That's a multiple access channel, where it was showed that then sharing an entangled state at the senders, it increased the capacity even for the classical model. And we want to find out if this is also the case for the dual, because there are a lot of results where you have the same capacity like for the Gaussian channel, Gaussian broadcast channel with a total power constraint where the capacities are the same. Then we also look at the case when we just have conferencing between the two decoders, between Bob1 and Bob2. That means they can transmit classical bits with a certain capacity. And the third scenario we will look at is the scenario if we have this classical conferencing and also the shared entangled state. And then, of course, we can do quantum conferencing. That means we can teleportate from Bob1 to Bob2. And then we can consider the case when Bob1 is only helping Bob2 to receive his message. So that means Bob1 don't have a goal to receive something, he's just helping them. And then in all three scenarios, so Bob1 is somehow acting like a relay. And in the last scenario I told you, when we can teleport the state from Bob1 to Bob2, then we have somehow here, then Bob1 is some kind of a repeater sending something to Bob2, and here the direct connection between Alice and Bob2 is somehow the repeaterless connection. And we can compare how we can use them and what we have to use. So first I want to start why we need quantum repeaters somehow. So in general, attenuation in optical fibers poses a great challenge for long distance quantum communication protocols, because we cannot amplitude the signal in quantum communication. And we have this application, quantum key distribution, and there we want to distribute a key, and then we can use this key as a one-pad encryption. But therefore we need to run this protocol over long distances, and so we need shared entanglement via long distances. And we have a recent book on quantum networks, where we also look at general quantum networks and how shared entanglement can be used, also not for QKD, but to increase capacity and to use it for identification and other things. So somehow it's just a mostly theoretical toolbox which can be used now, which can be found in this book here. One potential solution to solve this problem are quantum repeaters, which were introduced by Briegel et al. In 1998. And the idea is that the distance is divided into smaller segments with quantum repeaters at intermediate stations. And Harald is also part of several projects running from the BMBF, where the goal is really to finally build someone, a demonstrator of a quantum repeater. And there we have several platforms, quantum dots, trapped ions, and diamond color centers. And there's also a white paper, which is called Extending Quantum Links, which can be also found on arXiv, where you can already see what is possible and how far we are. And this project ended now in July. This Cooling X it was called, and it will be continued as QRX. And so the people will now go, the physicists will now go into the field. Before they were more working in the labs. So this project started already in 2010, I think, and a lot of basic research was necessary to rise the status we have now. Why is straightforward amplification not possible? That's because of the no cloning theory. That means universally copying of quantum states stands in violation to quantum mechanics. What is the short idea of the quantum repeater of the first generation? What we want to realize somehow in this project? The idea is this here should be the quantum repeater, which have two states, P1 and P2. And here is the sender, and here somehow is the receiver. So this is Alice, and this is Bob. So we want to use quantum communication and entanglement distillation to prepare a state, an entangled state between the sender and the receiver, this here, between A and P1, and entangled quantum state between the repeater and the receiver, this state here between P2 and B. And then the repeater teleports the quantum state P1 onto B1. So we have a swapping of the entanglement, and then finally A and B1 are now entangled at twice the distance. So that's roughly speaking the idea of a quantum repeater. And then the final idea is to have entangled state over long distances, to have many repeaters in this line and create in this way entanglement. And then you can run the QKD protocol, for example, or also other protocols. Just to give you an idea about information theory. So normally, also in classical channels, the communication relies on error correcting codes. So that means we have a noisy channel. So in classical communication with some probability, if you send a bit, with some probability you receive the correct bit, or with another probability is the wrong bit. And so to have error-free or near error-free communication, you need to introduce some redundancy. So you need to introduce error correcting codes to reduce the probability of decoding error. And in information theory, then you look at the coding rate. So K is the number of information bits which you can transmit, and N is the number of transmissions you need for this. And Shannon, in his work in 1949, he gave a formula for the classical case, the channel capacity, and this is just the highest communication rate if the number of transmission goes to infinity and the error probability goes to 0. And this is a really nice formula. It just is a single letter formula, which is easy to compute with about the mutual information. So it's a simple single letter formula. So for the capacity for quantum channels, we have different categories. So first, we can think about just to transmit classical information over the quantum channels. And therefore, we get the classical capacity. This was done by Holger in 1998 and Schumacher and Westmoreland in 1997. And this is transmission of classical bits using a quantum channel. Of course, what you can also do, we want to transmit qubits, so quantum bits over the quantum channel. And then you get another capacity, that's the quantum capacity. This was done by Lloyd, Shor, and Devetak. But unfortunately, you get a multiletter formula. That means you remember our n goes to infinity. So we have to normalize by 1 over n, and we have to calculate the limits. And this is always difficult to calculate. But it gives you, at least it gives you some lower bounds, of course, if you don't calculate the limit there. Then there's the idea of Bennett to use the entanglement to calculate the entanglement-assisted capacity. And first thing that what he shows that we get a strictly higher capacity, and the nice thing is we get like in Shannon's case a single-letter formula. And even in the but in the classical channel, it is shown also by Bennett in the same paper that the entanglement resources do not help. So that means the entanglement resource always means that the sender and the receiver shared an entangled state and can use this for communication. Then there was last year somehow surprising result that entanglement resources between two transmitters can increase achievable rates. That means the MAC, as you remember before, that's the dual channel of the broadcast channel. So we have two senders and one receivers. And even in the classical case, if we have an entanglement resource of the two transmitters, the capacity increase. And the idea comes from Nötzel, Winter, and Quack and Shor. So they use a channel which is defined by a pseudo telepathy game, like the CSHAS game. And there are some related works to our work. So first, this is a related work that's somehow the classical version. If you look at classical broadcast channel with cooperation, so the degraded case was solved by Dabora and Servetor, and the non-degraded case by Steinberg. And there are several other papers which consider quantum network channels and some resources. I uploaded in the Slack our paper, and there you find more references. So we, as I already told you in the beginning, we consider now a quantum broadcast channel in different settings. So we will start with entanglement resources at the two receiver. Then the second thing, we do classical conferencing. That means receiver 1 can send a classical message to receiver 2. And then we do quantum conferences. That means receiver 1 can teleportate a quantum state to receiver 2. So, and then if receiver, we also consider the primitive relay channel. In this case, receivers, the goal of receiver 1 is not to receive a message. He just serves receiver 2 and help him to receive his message. So the first observation is there's a trade-off between repeater-added and repeater-less communication. And we will show there's a bottleneck behavior of the repeater. So perhaps shortly to remind you, a quantum state is a vector in a Hilbert space, and a qubit is just a 0 state here, or the 1 state, or it even can be in superposition. And two states are entangled if we cannot write the joint state as a tensor product of the single states. And the maximal entangled state, I think you know this, is this one here. And now we can define the von Neumann entropy like we do it in the classical case. And then we can also define the conditional entropy. And if you are used to work with information theory, you will remember that this in classical information theory is an identity. So you define normally the conditional entropy by averaging over probabilities. That's not possible here. And so one uses the identity here as a definition. in this case, if you look at this maximal entangled state here, the entropy of it, because you know everything, so the entropy measures somehow the insecurity of the state, is 0. But if you look at the states of A and B, then it's 1, because with probability 1/2 you get 0 or 1 if you measure it. But that means that in this case, the conditional entropy is -1. So that's very special in quantum information theory, because in classical information theory, the conditional entropy never can be negative. Therefore, we introduce a special name for this. So mutual information is defined as usual, and this one here is called the coherent information. And a quantum broadcast channel, we want to look at this now, is a linear, completely positive, trace-preserving map corresponding to a quantum physical evolution. So we have an input state here, and the output state is this joint state here, and Bob1 have access to the system B1 and Bob2 to the system B2. So let's first start with our first case. The first case is if Bob1 and Bob2 shared an entangled state here. And what is now a classical code for the quantum broadcast channel with degraded message set? So it's called 2K0, 2K1 encode. So that means we have 2 index sets. One goes from 1 to 2 to the K, 0, and the other goes from 1 to the 2 to the K1. And we have this encoding map where M0 and M1 are the common and the private message, respectively. So that means they both want to recover the common message, and Bob1 also the private message. And we have as a resource this pure entangled state here. And we have two measurements of receiver 1 and receiver 2. One is denoted by lambda, and the other are denoted by gamma. So how is the communication scheme? Alice chooses a common message M0 for both users and a private message M1 for Bob, and then prepares the state here and transmits the state. And the output is that Bob1 and Bob2 receive their states B1n and B2n here. And Bob1 combines it with this shared entangled state and performs the measurement lambda. And similarly, Bob2 can perform his measurement gamma on his state and the shared entangled state. And then we can calculate the probability, the error probability that the decoding is wrong. So the coding rate, again, we have 2 rates here. We have the common rate, that's K0 over n, and the private rate, that's K1 over n. And we call a rate pair R0, R1 achievable with the entangled encoder if we have a sequence of codes such the proper error probability goes to 0 for all M0 in this set and all M1s in this set here. And the channel capacity is defined as a set of achievable pairs with the entangled encoders. And the first question I asked in the very beginning is, there's this duality of the broadcast channel and the multiple access channel. And we have this result from last year that entanglement between the two transmitters can strictly increase the achievable rates, even in the classical case. And the first question is, does the dual property hold? And the answer, perhaps it's obviously, so it's not so difficult, is no, because somehow it's clear if you do it for a Mac, then you have some influence or correlation with the channel. But if you do it for the broadcast channel and you have the entanglement at the receivers, there's no influence to the channel at all. So I think you cannot expect something. And so we also proved that the channel, that the capacity reason of a broadcast channel with entangled decoders is the same as without entanglement resources. Now let's go to the second setting. So we look now at the case if we have conferencing. So now Bob1 is allowed to transmit some classical bits with this rate C12 to Bob2. So he has the set here and can transmit something with this rate to Bob2. Then we can define this rate region here. So I have to, and you see here, this is typical for the broadcast channel where you use auxiliary variables. That's also how we get this region here. But we can bound the cardinality of our auxiliary random variables. Sorry. So x0 is bounded by this cardinality, and x1 is the cardinality of x1 is bounded by this cardinality here. And then our result is that the classical capacity region of the quantum broadcast channel with conferences and degraded message set is given by this capacity here. Unfortunately, you see again, you have a multi-letter formula. The good thing is, if you just look at the Hadamard broadcast channel, that's a generalization of the degraded classical broadcast channel, then we get a single letter formula. Then we get just this result here. And the ideas are very similar, like in the, the achievable part is similar to classical coding. So it's a classical construction. So we use superposition coding and binning. And the bins are indexed by the conference method G. And we use a quantum packing lemma, the square root measurement, and an idea of my co-author, which he used in 2020, that he do some gentle measurement, use some gentle measurement lever to perform consecutive measurements without collapsing the output. Now we do some quantum conferencing. So that means now, from now on, we assume that we have both. We have this shared entangled state, and we also have quantum conferencing. And therefore, Bob1 can teleport a quantum state to Bob2 at this conferencing rate here. Because we have this, we have restrict here our classical rate, which can be used by Bob1 to send information to Bob2. So so because of the no cloning, the receivers cannot recover common quantum states, and so thus we have to consider two private messages M1 and M2. And here you see the measures are different. These are qubits by transmission, and these are bits by transmission. See a classical bits by transmission, because this is the rate for the classical conferencing, and this is how somehow the rate for the teleportation. Also, more general subspace transmission is possible. So quantum communication is also referred as entanglement transmission and can be extended to strong subspace transmission, where the entanglement between the message system and the environment is also recovered. And also what we can do is entanglement generation, but by the monogamy of a property of quantum entanglement, it's not possible that Alice can generate a maximal entangled state with Bob1 and Bob2. But what Alice can do is she can generate a GHZ state, like here, we have it before in the talk also. And also the other possibilities, she can use two auxiliary states and generate entangled state between Bob1 and one entangled state between Tor, and takes the tensor product of them. And our theorem is now that we have the following achievable region here. So in terms of coherent information, and here you see again we have this auxiliary systems here, A1 and A2, like we have the auxiliary random variable in the classical case. And the observation is that the rate region reflects a greedy approach. We are using the conference link to increase the information rate of user 2. That means we, if Q1 is equal to the coherent information between the auxiliary system A2 and B2 plus delta, then we have here for Q1 this coherent information minus delta. So the next observation is for classical information, the optimal performance is achieved using a superposition coding, as you see before, where receiver 1 can recover the message of user 2 without losing rate. But for the quantum scheme, it's not involves superposition. So without conferencing, it is impossible for receiver 1 even to decode the message of user 2. Otherwise, we have a contradiction to the no cloning theory. And the third observation is the setting of the conference decoders in post chronological order. First, Bob1 receives his state B1 to the end. Then Bob1 sends a conference message to Bob2. And at last, Bob2 receives his state B2n and sends a conference message. And hence, Bob1 can recover the state of M2 and send it to Bob using the conference links while destroying then the state in his location. We also have an outer bound for this. Perhaps I have to go a little bit faster. So, and now the last thing is now what we can do is in all the settings, we can say the goal of Bob1 is not longer to receive something. He just want to act as a relay. So he just want to support Bob2 to receive his message. So his task is only to help the transmission of information to Bob2 here. Then you have some kind of relay here. So, and then we can do this for the case. Let's now just consider the case where we have this quantum conferencing here. There we have a cut set upper bound here. That's this one here. And we have a decode forward lower bound. That's this one here. And the third idea somehow comes from Mario Berter, that we have an entangled formation lower bound. And in this case, this proof is just, so the achievability is based on channel simulation. So somehow there's a channel simulated going over the relay. And the observation is, so we can use an Alice Bob1 and Bob2 as sender, repeater, and destination receiver. So the repeater is somehow the quantum version of a relay. And our results show the trade-off between repeaterless communication and relaying information through the repeater. So if you look at the decode forward lower bound, then this term here is somehow the link which corresponds to the repeaterless communication, because that's the link which goes directly from the sender to Bob2, so from Alice to Bob2, and while this link here corresponds to the quantum transmission via the repeater. So, but here you see also the bottlenecks flow, because we have the serial connection between sender repeater link from A to B1 with a repeater receiver link from B1 B2. So the throughput is now dictated by the smaller rate. You see here, this is somehow the quantum conference rate, and this somehow here is the rate which can be sent from the sender to Bob1. So thank you for listening.